Welcome back to the deep dive. We're continuing our journey through the online encyclopedia of integer sequences, aimed especially at number theory students.
That's right.
And today we're tackling a really, truly foundational sequence.
Which one is that?
It's OEIS A000217, the triangular numbers.
Ah, yes. The
Yeah.
classic. You really can't get much more fundamental than the triangular numbers. They're everywhere.
Exactly. So let's start with the basics, the definition. The OEIS gives us AN equals n times n plus 1 divided by 2.
Mm-hmm. The sum of the first n integers starting from 1, or 0 if you prefer n0.
Right. And it's also the binomial coefficient n plus 1 choose 2. You see that notation?
Yeah.
Cn plus 1, 2. Sometimes 2.
And Tn is common as well. T for triangular.
Good point. And about that starting point, the OEIS lists the first term as 0 for n0 0. So 0, 1, 3, 6, 10, 15, 21, 28. It goes on, of course.
Including 0 is sometimes algebraically convenient, makes certain formulas cleaner. But often, especially in combinatorics, starting with 1 makes more intuitive sense. The first triangular number is just 1.
Yeah, the sum of the first one positive integer. The sequence in the OEIS entry has offset 0, 3, which sort of flags both conventions.
Precisely.
Now, I think many people's first, maybe unconscious encounter with this is the story of Gauss, right? Summing numbers as a kid.
Absolutely. Summing 1 to 100. He essentially rediscovered or maybe just intuitively grasped the formula. nn plus 1, 2. It's a great illustration.
It really shows how a potentially long sum collapses into something neat. But the idea is much older, isn't it?
Oh, much older. You have to go back to the Pythagoreans. They were fascinated by the links between numbers and, well, geometric shapes. Figure numbers.
Shapes made of dots or pebbles.
Exactly. Arrange dots in layers to form equilateral triangles. 1 dot on top, then a row of 2 below it, then 3.
Okay, so the total number of dots gives you the sequence. 1, 1 plus 2, 3 plus 3 plus 3 is 6 plus 4x.
Precisely. It provides a wonderful visual intuition. That's where the name triangular comes from.
You can almost see the formula emerging. And it's great for teaching, too, maybe using multi-link cubes or something.
Definitely. You physically add the next row of n cubes to the previous triangle, Tn1, to get Tn. It makes the recurrence relation Tn plus n really obvious.
Okay, so definition, history, visualization, checked. But the really stunning thing, and this is where the OEIS entry just explodes, is the sheer number of places these numbers appear.
It's quite astonishing, isn't it? The diversity of contexts.
It really is. Like combinatorial interpretations, the number of edges in a complete graph can n plus 1.
Right, a graph with n plus 1 vertices where every vertex is connected to every other one.
How does that work out?
Well, think about adding the n plus 1 vertex. It has to connect to the n vertices already there. So you add n new edges.
So you're adding 1 edge, then 2 edges, then 3. Adding n edges at the nth step, it's a sum again.
Exactly. The structure grows in the same way the sequence does.
Okay, cool. Then there's something about parentheses.
Yes, the number of ways to legally insert one pair of parentheses into a string of n letters. Like for ABC, you could have ABC, ABC. That's 2 ways. Wait, is that right? Let me think. N3, AN is TN. Maybe TN1.
Let's check the OEIS note. String of n letters. For N3A3 equals 6, that seems too high. Maybe it's a different indexing. The note says TN1. So for N3, T2 equals 3 ways. ABC, ABC. No, just one pair.
Okay, let's pause on that exact interpretation. The core idea is it appears in string manipulation too.
Fair enough. Sometimes the indexing or exact formulation in these brief OEIS comments needs careful checking. But yes, it shows up there.
How about this one? Genus of a non-singular curve of degree n plus 2. That sounds advanced.
It is. We're talking algebraic geometry now. The genus is a measure of the topological complexity of a surface, sort of the number of holes.
And that's related to Tn.
For n greater than or equal to 1, yes. Tn gives the genus for a curve of degree n plus 2. It's a deep connection between simple counting and complex geometry.
Wow. And it's also a bound related to Harnack's theorem on the number of branches of a curve. AN 1 plus 1 in that case.
Okay, let's reel it back to slightly more tangible things, perhaps.
Dominoes. The number of tiles in a set of double N dominoes. Think about a standard double 6 set. You have pairs, 0, 0, up to 6, 6. How many unique pairs, allowing repeats like 5, 5, but not caring about order like 1 or 2 versus 2, 1?
It's like choosing 2 numbers from 0 to n with replacement allowed.
Exactly. Which turns out to be equivalent to choosing 2 distinct numbers from 0 to n plus 1, because n plus 2 choose 2, or t and n plus 1. Yeah. So for double 6, n6, t7 equals 782 equals 28 tiles.
Clever. Okay, another one people might know, handshakes.
Ah, the classic party problem.
Yeah.
If you have n+1 people in a room and everyone shakes everyone else's hand exactly once.
The total number of handshakes is Tn. The first person shakes n hands, the next new person shakes n1 new hands, and so on. Down to the last person making no new shakes. Sum of 1 to n again.
Precisely. It's a great intuitive example.
And the list goes on. Permutations, avoiding patterns, ternary words with restrictions, selecting numbers from sets, transpositions in symmetric groups, terms in polynomial expansions.
Dimension of orthogonal groups, positive roots in root systems, number of triangles formed by Sivians.
Number of solutions to x plus y plus z equals n1, matches in a round-robin tournament.
It just keeps appearing. It reflects a fundamental counting principle.
Absolutely. Let's switch gears a bit to number theoretic properties. These are often just as fascinating.
Agreed. There are some really elegant relationships.
Like the conjecture that only 1, 6, and 120 are both triangular numbers and factorials.
Right, Brocard's problem in a sense, but for triangular numbers, n nu pm, it's believed those are the only solutions. Shows how different these sequences are, generally.
Here's one I love. Add any two consecutive triangular numbers.
And you always get a perfect square.
Yeah. Tn plus 1 n plus 1 plus 1, 2. So 1 plus 3, 4, 22. 3 plus 6, 9, 32. 6 plus 10, 16, 42.
It's beautiful. Algebraically, n plus 1, 2 plus n plus 1, n plus 2, 2 simplifies nicely. Visually, you can see two triangles fitting together to make a square.
That visual is great. Then there's a link to perfect numbers.
An even number is perfect if it equals the sum of its proper divisors. And Tn is an even perfect number if and only if.
N is a Mersenne prime. So if 2p1 is prime, then T2p1 is a perfect number.
Correct. Like for P3, 23, 1 is a prime. T7 equals 28, which is perfect. 1 plus 2 plus 4 plus 7 plus 14 plus 28. For P5, 25, 1 equals 31, prime. T31 equals 496, the next perfect number.
That's a really deep connection. What about cubes? I saw something about cubes.
Yes. Any perfect cube, n3, is the difference between the squares of two consecutive triangular numbers.
How does that work?
It's Tn2, Tn12, so T22, T12, 12 by 1 was 23, which is 23. And T32, T22 is this 2, T2, 32 equals 36. 9 is 27, which is 33.
Wow, that's neat. And the OEIS lists many other identities, recurrences.
Oh, tons. The basic recurrence Tn, Tn1 plus n is key. There's also Tn, Tn1 is 2 plus 1.
And properties like Tn is congruent to 0 or 1 mod 3. Divisibility rules, connections to generating functions.
Ordinary generating function is x, 1 by 3. Exponential generating function involves x. There are Dirichlet series continued fractions. It's a rich area.
It really feels like a sequence you can explore endlessly, and it's also connected to polygonal numbers more generally, right?
Yes, triangular numbers are the simplest case, 3 sides. Then you have square numbers, 4 sides, pentagonal, 5 sides, and so on. They all have related formulas based on adding layers to geometric shapes.
Now, something quite interesting I saw mentioned was about sums of consecutive triangular numbers.
Yes. When is a sum like Tn plus 1 plus Tn plus k nice 1 equal to another triangular number, say Tm?
Exactly. There was a paper mentioned exploring this. Apparently for K2, two consecutive terms, we already know the sum is a square, which is rarely triangular. For K3 and K5, there are infinitely many solutions.
Right. But surprisingly, for K4, there are no solutions. A sum of 4 consecutive triangular numbers can never be triangular.
No solutions at all. That's unexpected.
It is. And things get even more interesting. A theorem states that solutions do exist if k, the number of terms, is a perfect square greater than 4.
So for K9 or K16, there are sums of 9 or 16 consecutive triangular numbers that equal another triangular number.
Correct. But another theorem counters that, saying that for almost all values of k, there are no solutions.
So solutions are rare overall, except for these specific square values of k and K3, K5.
Precisely. It's a fascinating constraint on these sums.
Moving towards applications, these numbers are fantastic for teaching, aren't they? NRAOCH has loads of examples.
Absolutely. Gauss's method is a great starting point for arithmetic series, the multi-length cubes for visualization.
And exploring Tn plus Tm plus 1 plus 1, 2 visually, seeing squares emerge.
Also problems like mystic rows, drawing lines between points on a circle, or this handshake problem we mentioned, they all lead naturally to triangular numbers.
Yeah, those are great icebreakers or starter problems, and they help bridge the gap from just seeing the pattern 1, 3, 6, 10 to understanding the n plus 1, 2 formula.
That leap from the recursive idea, at the next number, to the closed form formula can be tricky for students. Visual and contextual problems help a lot.
They connect it to quadratic sequences too, algebraically.
Right. And even things like probability sample spaces for dice throws can sometimes be visualized using triangular grids.
I also saw a mention of a puzzle from Mathematics Magazine, joining digits 1 and 3 to make 13.
Ah, yes. It's a puzzle whose solution can be modeled using either triangular numbers or combinations, leading to the same answer through different conceptual paths. It highlights how different mathematical tools can tackle the same problem.
That's a nice illustration of, well, mathematical connections again.
Indeed.
So wrapping up our dive into ES A000217, it's clear that triangular numbers are far more than just sums of integers or dots and triangles.
Absolutely. They are fundamental building blocks appearing in, well, combinatorics, number theory, geometry, graph theory. You name it.
Their simplicity is deceptive. The OEIS entry really showcases their richness and ubiquity.
It's a perfect example of why the OEIS is such a valuable resource.
Yeah.
You start with a simple sequence and uncover this vast web of connections.
We've seen the definition, the visual side, the combinatorial explosion, the number theory gems, classroom uses.
And even puzzles and specific theorems about their sums.
For anyone listening, definitely explore A000217 on the OEIS website. Follow the links, look at the references. It's quite a journey.
You're guaranteed to find connections you didn't expect.
So here's maybe a final thought to leave you with. We've seen how incredibly widespread these simple triangular numbers are. What other sequences, maybe ones that seem just as simple on the surface, might be hiding similarly deep and surprising connections across all of mathematics?
And perhaps thinking about that sums of consecutive triangular numbers result.
Yeah.
Why are solutions so rare, even though they exist for specific cases like squares? What does that tell us about the deeper structure?
Good questions to ponder. Definitely something to think about.